A cerebral capillary has a diameter of 3 micrometers and is 625 micrometer long. Given that the viscosity of the blood in the capillary is 3.25 times 10 to the minus 3 Pascal seconds, what resistance to blood flow does the capillary present? And if it has blood flowing through it with a volume flow rate of 8,836 micrometers cubed per second, what is the pressure drop? So let's go ahead and start with the resistance to flow rate. We're going to use the Poisson model for this. It works in many cases for blood flow because blood flow is not very fast. Poisson flow tends to break down when flows get fast, but in this case it's probably not that fast. So the formula we're going to use is 8 eta for the viscosity, L for the length of a pipe or capillary in this case, divided by pi r to the fourth, where r is the inside radius of the pipe in question, in this case again, the capillary. So I think I could probably just identify the correct physical quantities to input into this formula looking directly at the question here, because the viscosity is given to us. So we'll start with that of 3.25 times 10 to the minus 3 Pascal seconds. And then we have L in the formula here. That's the length, but that's also given to us as 625 micrometers or micron. I'm going to go ahead and put that in as 625. I'm going to work in micrometers. Oops. Let me make sure my micrometer notation is decent enough looking. Okay, so we'll put that in that way. And then we're going to divide by the pi that's in that formula, and that's radius to the fourth power. We're given diameter, so that's a easy thing to get tripped up on. Is that means the radius is 1.5 micrometers, not the 3, because that's the diameter. Whoops. And then we need to raise that to the fourth power. And we can put this into the calculator, and the calculator says 1.021735437. I could probably round that off as a final answer. At least I could round that off to 1.02, since it looks like we're kind of at a 3 sig fig level here. And appropriate units looks like they would be Pascal seconds divided by micrometers cubed. So put that in there. Okay. And now, since we're also asked for the pressure drop, that's probably the thing we'd really be interested in here, is to know what the pressure drop is. I'm not sure why we'd be interested. Maybe for a researcher in life sciences that looks at capillaries, maybe there's a reason this would be interesting. Since we know that delta P is equal to volumetric flow rate times flow resistance, and we're given that volume flow rate of 8,836 micrometers cubed per second, I'm just going to plug that in here and say, okay, that's the number we're going to put here, 8,836 micrometers cubed per second, and then I'm going to put in the 1.02. Although, since this is a plugin that is already rounded here, I might want to keep a few more. Maybe if I do at least one more digit, would have been another 2, I think, from what I stated earlier. Or if you still have that stored in the calculator, you could reference it, which I'm going to wind up doing. But I don't want to have to write that whole number out, so I just put in one more digit, so I'm avoiding round off error. So you can check how close you get to what my result is, because my calculator says 9,028 and etc., and I'm just going to round that off to 9,030. And if everything works out, this should be a pressure, right? So the micrometers cubed here cancels against that one. This second down here cancels against that one, and the only remaining unit is the Pascal, which is a unit for pressure. So in that sense, these two things here are my final. Oops, final answers. I think I kind of obscured the 1 on that one there. Okay, well, I'll remember that was a 1.02, right? Let's go and check it. 1.02 Pascal seconds per micrometer cubed and 9,030 Pascal.